Okay, welcome back all. We're ready to start our afternoon session. We're going to have two groups of talks on the topic of air quality modeling for health and regulatory assessments. In our first session, we have a number of speakers, including our first speaker, our invited speaker, one of our invited speakers. We'll have one virtual talk. Please feel free to put questions in the Slido website as the talk is occurring, and then we'll also open it up for questions from the floor after each speaker. So it's my pleasure to introduce our first speaker, an invited speaker, Minghui Diao. She was associate professor, at San Jose State University. She received her bachelor's degree at Peking University and PhD from Princeton University, and she uses observations and models to support air quality and health assessments in California. And I'll turn it over to her for a talk.
Hello, everyone. Thank you for coming to this session. So the title today I have is Integrating Earth System Modeling and Multi-Scale Observations to Support Health Studies in California. I want to thank the committee member for inviting me to this talk, and also thank my most recent collaborators for helping me establish some of the groundwork. So we're currently funded by 2 DOE projects, and several years ago, we used to be part of the HACUST team. So this is a brief outline of my talk today. I'll start with a survey of the traditional approaches to provide estimate of PM 2.5 for retrospective health analysis. This is more like what do we have right now and what are the existing challenges we have been seeing for decades. And the second part, as we all know, it's important to produce community scale PM 2.5 estimates. So we will present a method that we were funded by the NASA HACUST project to integrate NASA satellite observations with ground-based monitors towards a community scale resolution. Now, the third part is some of the recent work. There's some very exciting advancement in the model simulation tools. So we have these high resolution climate modeling in California that can reach regional 3-kilometer simulation that could build a community scale climate resilience in the future. And lastly, I'll touch upon some of the wildfire impacts in California, the smoke health impact, and how do we connect observations and modeling on that perspective. So a motivational slide, as everyone here in this room know, we have PM 2.5 as probably the #1 most impactful air pollutants around the world. It is estimated to contribute to more than 4 million deaths about every year. And I just highlighted in this chart, you can see United States as a country seem to see a decline of the percentage deaths attributable to PM 2.5. However, this could be a little misleading because this does not represent the community scale nor the regional scale, considering the increasing wildfire activity in the west coast of the country. So the importance of providing the PM2 data set could support different type of health studies or decision-making activity, depending on if you have a looking backward retrospective analysis or forward-looking near future or decades in the future. And these can be important for stakeholders and communities for different activities. So the first part, I will go over a survey of frequency used PM 2.5 data and generation method as for health studies. I listed here 4 main methods that you can see in most of the literature that usually start with just ground-based monitor. These are usually considered as the golden ground truth for getting the most accurate PM 2.5 data. However, just keep in mind, even in California, which is the state that everyone knows most well-monitored state, I would claim, maybe it's not in the United States, it still only have some monitor, maybe only 1 monitor per county. So having a single location measurement just to represent the entire county, how fair that is, everyone can conclude it's not the best way to do health studies. But how can we provide a more spatially wide coverage by combining with model or satellite, and satellite model data has been a lot of the progress in the research field. So here we had a research article, it's a review article in January 2019. I collaborated with Tracy Holloway, Susan O'Neill, and several other co-authors. We compared 4 frequency use data set that are generated from either satellite plus monitor or model monitor or all of them versus just the EPA air data. To keep in mind, we only selected one year. This is only 2011. So this is not the most representative year for representing the accuracy of each data set, but that's the only year we have the overlapping data among 4 of them. And you can easily see that none of them actually agree with each other. And it's hard to put your finger and say that which one is obviously the best, because like I said, EPA data will sometimes have only one monitor representing a large domain. So guidance is still needed for users, especially from public health field, for them to access, interpret, and keep in mind of the challenges behind these data instead of only just downloading and using it directly. So here's another summary to show you if we add up all the data over the entire continuous US, that can show some of the CDC wonder data is an outlier. It has a high value, especially over central US, and Dalhousie data seem to have the lowest mean, et cetera, et cetera. So how do we move forward from here? And there are presented a lot of challenges. One thing I want to talk about is what about the community scale? So in the HACUS project, we were funded from 2016 to 2021. Our goal was to generate a 3-kilometer daily PM 2.5 field for entire California for about over 15 years. And this is a publicly available data. You can download it for free through just a few clicks on the HACUS San Jose State website. And we, at that time, also provided demonstration that you could provide a near real-time PM 2.5 data by integrating the NASA MODIS, the ICAR MODIS aerosol optical depth data with the EPA ground-based monitor. And here's another demonstration of some of the visualization tool that we provided by selecting days over San Francisco Bay Area. You can see the large spatial heterogeneity just in this small domain. And this goes back to the fundamental question, how can we support different communities for their decision-making, given that they face so much disparity in the amount of air pollution day by day, but also possibly in the next decade or next 50 years. So this is just a illustration. You can clearly see a hotspot in San Francisco airport if you flew in from SFO today or yesterday, or you can also see some of the hotspot right around here. That's actually the San Jose International Airport. So that is another plot provided by Bob Sheffield and Mater Solveig Hammer. They also did some similar statistical analysis to demonstrate the spatial heterogeneity. Now, moving on to the part 3 of my talk, I want to represent this new exciting technological development in the climate modeling group that I work with. So this is developed by my co-ide Xitang from Lawrence Livermore National Lab. To briefly mention the advancement is usually the climate model used to run at 1 degree for the entire globe. And now they have this regionally refined modeling that can run as 3 kilometers for the state of California, although everywhere else is still 100 kilometers. So this project is funded by the Department of Energy Climate Resilience Center, and we just received the funding like two months ago. And we also collaborate with a lot of stakeholders and community advisors, such as US EPA, CDC, et cetera, et cetera. And we're going to work with them step by step to get their feedback on how should we develop data product and provide different type of tools. So on the left-hand side, this big picture I have is the spatial heterogeneity of the poverty percentiles in California. And you can see even for Bay Area, which is supposed to be a pretty wealthy location in California, there's still a lot of people living with the poverty percentile about even 70%. And since we have a climate modeling tool, now we have a chance to not only represent the projection of air pollution in the next 10, 20, 50 years, but we can also consider a wide spectrum of climate impacts in conjunction to air pollution problems. For example, we face extreme heat, sometimes with a compounding effect with wildfire smoke. And we sometimes have severe weather shortly after the wildfire just hit California. So how can we capture not only a short time span, in just a matter of a few months, but in a matter of from the last 20 years to the next 50 years in decadal scale, can we afford this type of simulation and also provide a community scale estimate? So we seem to be asking a lot of questions from this climate model, but can we do that? So like I want to reiterate the point, we want to, on the one hand, achieve these high spatial resolution because of the distribution of air pollutants and also the distribution of social economical status is so spatially heterogeneous. So that requires high resolution from the model. And we also want to keep a two-way interaction for the physical process. So anything from the global domain, such as larger atmospheric river event or El Nino, any seasonal, sub-seasonal, or decadal fluctuation, we can still represent it. And then computationally, it has to be cheap, so we can actually afford to run it for a long time. And that actually can just be done from this E3SM regionally refined model that was just tested in, I think last year, December, the first simulation at 3 kilometers inside California was just achieved. So we have the 3 kilometer simulation. This is a demonstration when the original E3SM climate model funded by Department of Energy was run at 100 kilometer scale. You can see the topography of California just represented by maybe 20, 30 great bins. And then once we go to 20 kilometers, you can start to see some differences between the valley and the high mountains. And at 3 kilometers, just the topography already starts to be more realistic. And we can achieve 1 simulation month per wall clock day. So that means if you want to run a year, you will just have to run it for 12 days. It is still reasonably acceptable. So this is the project that we are recently funded, and this is the scope that we're thinking about moving forward. We want to link the global dynamical system at 100 kilometer scale with the regional model at 3 kilometer scale, but also we want to build a framework that can connect with the applied science model, such as the epidemiological model, and they will have the zip code or county level estimate of health benefits or health burdens. And we also want to build the climate model or nudge them using some of the state-of-the-art wildfires field observation to represent wildfire event with case-to-case scenario. Finally, the goal of all of this modeling observation integrated framework is to provide more mitigation and adaptation plans. One example is if in a hypothetical scenario, if we have one climate adaptation plans for installing more air conditioning in California, what would be the most impactful, most beneficial, and ethnical and environmentally fair way to install them on the community level. So this kind of question from stakeholders, we may be able to answer with this new framework. So lastly, I want to briefly mention the public health smoke study that we've been doing in the department. Back in the HACUS project, in this paper led by Susan O'Neill, we demonstrated how we can combine the EPA monitor with the NASA MODIS AOD product and provide an integrated observation field for a specific 2017 wildfire. And moving from this demonstration, in recent years, my department at San Jose State acquired several mobile observations, including I think this is the only K-band scanning cloud radar that is mobile on a truck for the west coast of United States that we can deploy to active wildfire or prescribed burn. And also there is a new Professor Adam Kochansky. He does the wildfire S-fire simulation that can be run at hundreds of meters of scale. So we want to use these observation or high resolution model to support the modeling framework that I just mentioned, such as a climate model. And this is an illustration of what it looks like from a real measurement during fire that's in 2013 or 2016 with the dispersion of the smoke kind of sampled in the Lagrangian view. And this is also near prescribed burn, the cloud radar scan of the reflectivity. On the right-hand side is the simulation from the DOE E3SM RRM model done by Xitang. So you can see black carbon and POM, how they're actually projected and dispersed from their sources. So lastly, as my conclusion slide, we demonstrated a survey to show you the existing literature approaches and the challenges for generating PM 2.5 data set. We've seen discrepancies among even the most frequently used data set by public health users. And second, towards building a community scale near real time estimate of PM 2.5, we try to integrate the NASA satellite data with the ground monitor data. That's the one way towards a 3 kilometer community level. But keep in mind, we cannot predict the future if we only integrate observations. So model is still very important if we want to forecast even the next day, next month, or next year. And 3, when we try to reach high resolution and long-term simulation that can approach both the past and the future, there is a new type of technology emerging from climate community that can connect the Earth system modeling with epidemiology models onto community scale for a specific region. And lastly, improving the model simulation, such as for episodic event of a wildfire, it is very difficult for the climate model to capture it by itself. So we want to use the observations provided by these mobile stations to constrain the model. And that way we can focus on a case of a wildfire and analyze the health impact. So with that, I want to show you all my current and past former students. I'm not all working on the aerosol direction, but they have been all over the country. If you see them, please say hi. And that is my research website. And I want to thank all the funding agencies from Department of Energy, NASA, NSF, Livermore Lab, and NCAR and SJSU. That's all for today. Thank you.
Thanks for a great talk, Minghui. So your work is really exciting in that you're integrating so many different data sets, and it's exciting moving in these high resolution climate simulations. But you also mentioned a few times interacting with stakeholders and what this means for individual communities. And so I was just wondering if you could speak to either any outreach or interactions you've already had with communities, or how you ultimately see when this project comes together can be used, or people can access this data, like real people who want to sort of get the end results of what you're doing, if that's sort of part of the end stream of the technical work.
That is actually a really great question, actually a critical question that we all often receive. I would say right now, I do see a barrier that a lot of the direct users of our product are stakeholders, especially stakeholders that are well educated and very motivated to use these data. And we have seen there's still like a gap that how do we translate this information to directly usable by the public? I think from the Wildfire Center that I've listened to some of their discussion, one method is to reach out to both the private sectors that may actually have a stronger influence on the community. For example, one of our stakeholders is from the I think the CSAA, the insurance company, and also some of the stakeholders of the Wildfire Center from PG&E, their action may immediately influence the community. And they also have introduced me to some of their diversity collaborators that have direct connection with the community. But yes, if anyone has suggestions to me how to provide a better pathway, direct dialogue with the community, that would be great.
Thanks.
Have you considered applying the same methodologies to think about pollutants other than PM 2.5 and perhaps the data sources and challenges associated with it, so ozone, NO2?
Wow, that's a great question. In fact, as part of this framework that we're trying to build, we have the capability to have the simulation of all the major chemical gases and the particulate matter. So it's not going to be a technical limitation. And we are interested in seeing some compounding effect if we have extreme heat and wildfire and the compounding effect of PM and goes on. So we're in a discussion with our health stakeholder and see how we can do that. Yeah, that will definitely be one of the direction we want to pursue. Thank you.
Thanks. I think for time, we'll move on to our next speaker. Let's thank Minghui. Our next speaker is Maninder. He's a research manager at the California Energy Commission and works at the nexus of air quality, human health, and California's clean energy transition. I'll turn it over to him.
Good afternoon, everyone. I'm delighted to be here. And today I will talk about my research work that I did during my PhD journey back at University of Washington, Seattle, looking at the environmental health, racial, ethnic health disparity, and climate impacts of interregional freight transport in the United States. Right, so I want to acknowledge the funding from the US EPA Center for Air, Climate, and Energy Solutions. And also this paper was published early this year in the Environmental Science and Technology journal. All right, so the research question that we looked at in this work is if a unit mass of freight is shipped from an origin to a destination, how do impacts on human health, that is health outcomes from exposure to PM 2.5 and climate, which is we looked at carbon dioxide emissions and exposure or human health disparity vary by the mode of travel. So we looked at the long-duty, heavy-duty truck, rail, barge, and aircraft. So across land, water, air, and rail. And we looked at around 30,000 routes distributed across the different modes of transportation. And so for health, as I mentioned, we estimate the PM 2.5 attributable mortality. And for climate, we estimate the CO2 emissions. And for health disparity, it was the difference between most exposed group and the population average. Right. So we chose the reduced complexity air quality model called intervention model for air pollution. INMAP is a reduced complexity air quality model that predicts the change in annual average PM 2.5 concentrations in attributable to change in annual emissions. INMAP is a high spatial resolution model that runs in a simple and computationally inexpensive way, and resolution varies from 1 kilometer by 1 kilometer in urban areas to larger grid cells in rural areas. So the model takes all the complex chemistry and physical parameters to convert emissions to changes in PM 2.5 concentrations. The concentrations are overlaid with the population estimates by race and ethnicity from the 2016 US Census database from where we got the data. And we quantify the health impacts attributable to long-term PM 2.5 exposure using a standard log linear concentration response function. For all-cause mortality from the American Cancer Society reanalysis work. The health metric used is the premature mortality from exposure to PM 2.5, and we use the INMAP source receptor metrics, which was developed running INMAP multiple times for each mode here for this work. And the OD pair, the origin destination pair, nationally and disaggregated by urban and rural areas. All right, so for the 4 modes we chose, We use the most current vehicle and fuel properties. We use the 2019 exhaust emission factors from the GREET model for primary PM 2.5, nitrogen oxides, sulfur dioxide, volatile organic compounds, and as well as the carbon dioxide emissions. And for truck, rail, barge, we use the low sulfur diesel with the sulfur content of 11 ppm. And for rail, we mainly use the low sulfur non-road diesel corresponding to 11 ppm sulfur. And for barge as well, low sulfur non-road diesel. For aircrafts, we used 4 types of aircrafts were modeled, as highlighted in the slide here, which are categorized based on the payload, average payload, and the average flight distance. And the aircraft emission factors differ for landing and takeoff versus for the cruise emissions. And we further separated the landing, takeoff, and LTO emissions into 5 categories, which are the taxi, idle in, and taxi, idle out, and approach and landing, takeoff, and the climb out. So that way for the aircrafts, we try to apply the emission factors based on the activity, whether it's on the runway or the cruise emissions. All right. So we studied, as I mentioned in the starting, the interregional transport, and which is not the intra-regional transport, so between the regions, which is composed of more than 16,000 OD pairs. And we run in map for each OD pair to compare between the mode and the route connecting, the origin and destination. So most, but not all, interregional freight transport is interstate. Our analysis assumes the shortest network route between origin and destination for road, rail, waterway, and the air routes. And annual emissions of VOC, NOx, ammonia, SO2, and the primary PM 2.5 are input to the ISRM for shortest routes as the line sources. The ground level ISRM grid is intersected with each route. And for the air, using the Great Circle path between the origin and destination. For routes, we use the geospatial information from DOT's National Transportation Atlas database, and information from tonnage, ton kilometer, and value of commodity flows between 132 designated regions of freight importance from the Department of Transportation's Freight Analysis Framework work. All right, let's now jump into some of the results that we looked. Right. So these are very dense plots with a lot of data. Each data point shows impact from a route, from an origin and destination. Impacts shown are, let's see. Yep. The impacts shown are deaths per megaton of payload and kg of CO2 emissions per megaton, and the risk gap per megaton in terms of deaths per 100,000 people per per ton of payload. And each of the subplot, for example, shows the comparison, the pairwise comparison between, for example, truck and rail. And we can see over here that for more than 99% of the OD pairs that we analyzed, the health impacts per megaton of the payload transported between origin and destination is greater for rail than truck, versus its opposite for the climate impacts we see in terms of carbon dioxide emissions. And for risk gap, for example, we see that For majority of the routes, the disparity is greater for the routes that are traversed by rail than the truck. All right, so to further explore the mode intercomparisons, we calculated average impacts across the OD pairs. We use both simple arithmetic mean or the simple average and the tonnage weighted mean or the weighted average across the OD pairs. One advantage of using both metrics is that the amount of freight of per mode or OD pair may change over time. So this shift would directly impact the weighted averages, but not the simple average. So here we see the three impacts together: average CO2 emissions, the total population mortality, and disparity in the exposure disparity in mortality as the icon size. So the impacts are per megaton payload, and we see the aircraft has the largest average and tonnage weighted health, climate, and exposure disparity impacts per megaton. Among non-aircraft modes, rail has the largest average and tonnage weighted health impacts and exposure disparity, and the lowest CO2 emissions. Among non-aircraft modes, truck has the largest average and tonnage weighted CO2 emissions and the lowest average and tonnage weighted health impacts. When we restrict the routes to 214 routes, which are common for all the four modes, the conclusions are similar, with the exception that if weighted by tonnage, rail has larger CO2 emissions impact than the barge. All right, so we disaggregate the impacts by urban and rural areas. We find that the truck, rail, and barge have modestly larger total health impacts to rural populations than to urban populations, reflecting that the majority of the highways, railway lines, and navigable waterways for interregional freight transportation travel through the rural areas, and which is partially counterbalanced by the large number of people in urban than in rural areas. And aircraft impacts are greater for urban than for rural populations, in part reflecting that most impacts are near airport and most airports are near urban centers. All right, so next, among the racial ethnic groups considered here, we estimate the impacts across the racial ethnic groups from all freight transportation, from the all freight movement, and also by different modes from truck, rail, barge, and aircraft. And we see that among racial ethnic groups considered here, the most impacted group in terms of risk per 100,000 people is white non-Hispanic from all freight transport. And this finding reflects in part because the rural truck travel as a major source of emissions, and these rural emissions are predominantly white and in the rural areas. And the most impacted group to rural populations by truck and rail is non-Hispanic white. If considered only impacts to urban populations, the most impacted group overall and separately for truck, rail, and barge is Black people. When considered by mode, the most impacted group for barge via water, by the navigable waterways, is the Black people, which is for overall population and urban and rural populations. And for aircraft, it's the mixed and other groups with overall and the urban populations. All right, so far we saw the climate and health are fundamentally different impacts. So we converted the climate and health impacts to monetized damages on a single scale. Here we do that conversion and comparison, recognizing the imperfections in hopes that the outputs lend insight into the relative impacts to the health versus climate. So to estimate monetary damages, in $2020, we use the social cost of carbon dioxide and as well as the value of statistical life derived from the US EPA as the mean of people distribution from 26 studies. And figure on the left over here shows the average monetary damages, total average monetary damages, and it's divided between carbon dioxide related damages and PM 2.5 related damages. And we see that the average monetized damages are largest from aircraft, followed by truck and rail, and lowest for barge. And damages from aircraft are considerable, like 4, 5, and 7 times those from truck, rail, and barge. And next, as a sensitivity analysis, we consider the impact of alternative values of social cost of carbon and the value of statistical life. Specifically, for the social cost of carbon, we imply 4 values, and for value of statistical life, we separately employ results from the 26 studies that were documented behind the estimation of the value of statistical life, which is documented in the US EPA's report. And this plot shows that while total damages depend on social cost of carbon and value of statistical life, pairwise comparisons between mode are relatively robust to variations in these numbers. Right. Finally, some of the conclusions mentioned over here: impacts in terms of health disparity, climate per ton of freight are largest for aircraft. Among non-aircraft modes per ton, rail has the largest health and health disparity impacts and lowest climate impacts, whereas truck transport has the lowest health impacts and greatest climate impacts. I think an important reminder that health and climate impacts are often, but not always, aligned. And to give an example, shipping companies usually incentivize the modal change based on the climate impacts, but it's also important to look at some of the health and also the health disparity impacts as well. And we see that there's a greater EJ, environmental justice concerns in urban areas from freight transportation. And also I want to highlight the importance of community-based groups and organizations in solving the disparities at the local scale, and also some of the efforts in electrification of the transportation to solve some of these issues at the nexus of climate, human health, and disparity. Yes, thank you. And I also want to thank my co-authors, Professor Julian Marshall and Chris, for contributing and helping in this work. Thank you.
Hi, great to see you. I'm curious if you think that by including the health impacts of these emissions via ozone or direct exposure to NO2 on premature mortality, that would affect any of the rankings that you're looking at between the health impacts of these different emission sectors?
Thank you for that question. If I understood correctly, you asked if we looked at the, in addition to PM 2.5, but also exposures to ozone and NO2 exposure. For this work, we only focused on the exposure to fine particulate matter. But we do highlight in our paper that, ozone and NO2 exposures are also important in terms for transportation sector, especially for certain geographies, for example, Colorado, Denver, and those certainly should be included, and that's also part of some of the future work that could be done from this work.
Let's thank our speaker one more time.
Thank you.
It's my pleasure to introduce our next speaker, Sue Meng, who is an air pollution specialist at the California Air Resources Board, and she'll be talking about the health impacts of air toxics.
Hi, everyone. My name is Sue, and I work in the regulatory risk modeling section at CARB. And today I will be presenting some of our team's work on health impact assessment of per ton of air toxics and its regulatory applications. And I know that our work here will be complementary to the work that my colleague Sarika will be presenting in a little bit. She will be focusing on the health impact of criteria pollutants, and we will focus on the impact of air toxics. Our team has been working on a project called California Air Toxics Assessment, or CATA. It is a high-resolution statewide assessment of health risk from air toxics, and it serves to bridge the scale between national toxic assessments, such as Air Tox Screen, previously known as NATA, and regional efforts, such as MATES in the South Coast. It also aims to support various air toxics program at CARB, as well as environmental justice programs. It is done on a triennial basis so that we can do trend analysis. Modeling has been completed for the 2012 and 2017 base years, and the modeling for 2021 is in progress. How can we apply this modeling work for regulatory needs? Because health risk assessment is typically required during the rulemaking process. And I hope that my talk today can convince you that CATA is not only a unique source of information for the public, but also for regulatory needs. To apply our work, we will use the metric of incidence per ton, or IPT, and it is useful for regulators to compare potential health benefits from different emission reduction plans in different regions and between emission sectors. First, a little introduction on how we did the CATA modeling. As I mentioned, we do the modeling every 3 years or so, and using the most recent emission inventory and meteorology. And so far, we've done 2012 and 2017. Today, for the presentation, I'll be mostly focusing on the 2017 modeling results, but also using the 2012 to do trend analysis. We estimated exposure and cumulative cancer risk for 12 air toxics, and we used 2 air quality models to assess the health impact from those air toxics. First, the cup-off air dispersion model to model diesel PM and heavy metals. So because dispersion models can have a better representation in space of the emission sources and the receptors. And then we used the CMAC for the chemical model to model the toxic VOCs. So by trading spatial accuracy, we gain a better representation of the chemistry and secondary formation of those. That's important for those VOCs. For meteorology, we used a 3-dimensional meteorology inputs from the WRF model at 2-kilometer grid resolution. And then we further categorized the emission sources of diesel PM and heavy metals into more than 30 categories. And that is very useful for regulations because we can compare different emission scenarios by source category and do source apportionment of the total risk in a region. The more details on those categories, first we have on-road mobile sources, which we modeled as road-following line sources. And then we have some of the off-road mobile sources, such as ocean-going vessels, or OGV, and aircraft that we modeled as long polygons that represent the activity corridors. And then the rest of the off-road, mobile, and area sources, we modeled them as 1 by 1 kilometer gridded sources. And then finally, for stationary sources, such as refineries and power plants, we model them as point sources. Now let's dive into the modeling results. So first, the air quality models will estimate the exposure from the annual average concentrations of the air toxics. On the map on the left shows an example of the diesel PM annual average concentrations for 2017. And then from that exposure, we estimate cancer risk, which is the probability of a person getting cancer from a continuous exposure to an air toxic throughout their lifetime. And we estimate that using the OEHA risk assessment guidelines. And so on the map on the right shows the 2017 total cancer risk scoring in terms of percentile for the census tracts in California. And so one tract with a scoring of 90 would mean that that tract is in the 90th percentile of all risk values throughout the state. And so we can see that disparity is still very much present throughout California, with high risk areas concentrated along the transport corridors and near the border. So now that we've seen what our modeling was conducted and some of the results that we can get from that modeling, now I'm going to how we can apply those model results for regulatory needs. And the metric I'll be using is IPT. And IPT was originally used by the US EPA for the number of premature deaths by total emissions. And here we will borrow that concept and by defining incidence as population-weighted cancer risk or cancer burden, which is cancer risk multiplied by population and divided by total emission. That gives us a metric that can quantify the complex relationship between the emissions and its health impact with a simple equation. And that's very useful for regulatory needs because it provides a quick but also accurate estimate because it comes from a full health risk assessment. So a quick estimate of the health benefit that will result from an emission control measure for a specific region and source type. And it can be used to compare emission reduction scenarios and also estimating future projection of health benefit from a certain emission reduction. On this bar chart shows the IPT values that we obtained on the statewide level for the 2017 diesel PM sources with the categories listed on the y-axis and the IPT values on the x-axis. As we can expect, the sectors that have lower plume rise and typically found near densely populated areas, such as on-road and off-road mobile sources, have higher IPT values. So there's larger impact from those emissions compared to, let's say, OGV and agriculture, which are typically found farther from the population. And that also means that the sectors with higher IPT values can give higher health benefit if we reduce emissions in those categories. Let's take a look at a more region-specific assessment. So the main message from this table is that there is a large variability that the IPT values have across the source types and regions. So we have the categories on the rows and 6 air basins on the columns. One thing we notice is the IPT values tend to be higher for smaller domains, such as the San Diego and Imperial regions. And that's because the IPT values in those smaller domains represent the more localized impact of the emission sources. And then something else that was specific to Imperial was the presence of inland canals that went through very densely populated areas. And that's why sectors like commercial hovercraft and cargo handling equipment had much higher values than in other basins. But in general, the IPT values are still higher for the on-road and off-road mobile sources, like what we saw for the statewide level. A more concrete example of how we can apply those values for regulatory needs is let's imagine a scenario where an OGV at birth regulation in the county of San Diego proposes a diesel PM emission reduction of 10 tons per year. We estimated an IPT value of 0.6 for San Diego for the OGV at birth sector. And so by using the simple relationship that we found by conducting the full modeling, we can estimate that the resulting cancer risk reductions at the county level will be about 6 chances per million people from that regulation without further modeling. And the same concept can be also applied on the community level. But we did see that it is highly dependent on scale. And so as you can see here as an example, I'm showing the IPT values for the portside community in San Diego on the table on the right. And then we also have as a reference the county level IPT values for San Diego on the left. And you can see that the absolute values of IPT are significantly different. And it's higher for the smaller scale because it is more concentrated and we're looking at the receptors that are really close to emission sources. But you can also notice that the relative importance of the sectors in terms of health impact is consistent. So, for example, we would achieve a higher health benefit from reducing emissions from locomotives than, let's say, maneuvering. We also looked at how the IPT values changed in time by comparing the modeling results between 2012 and 2017 for the diesel PM on-road sources. The IPT values are on the y-axis and then air basins on the x-axis, yellow bars representing 2012 and green bars representing 2017. And we can see that there's not much change between the 2 years, suggesting that there's not much change in the dispersion conditions and meteorology. So in conclusion, CADA is an ongoing initiative at CARB designed to assess the exposure and health risk from major air toxics on a triennial basis in California. From the CADA results, IPT values can be calculated, and it's a metric that simplifies the complex and nonlinear relationship between emissions and health impact on population. Those values are best used as relative values. It can be used to compare the effect of regulations. For example, where can we reduce emissions to achieve the most effective risk reductions? It can also help predict future health benefit from a regulation or policy. And as we saw, IPT values can differ significantly across scale, regions, and emission sources. For community level applications, for example, to inform community emission reduction plans or SERPs under AB 617, one should use the results at that scale and location. And we also saw that on-road diesel PM IPT values remain similar between the 2012 and 2017, suggesting that there's not much change in dispersion conditions. And lastly, I'd like to note that our goal is not to replace any full health risk assessment for a given regulation. On the contrary, we want to highlight the large variability that exists between scale and location and source type in the relationship between the emissions and health impact. We also acknowledge that a full risk assessment modeling takes a lot of time and computer resource. And so if you think that our work can be beneficial to you, please reach out for us. We have a report that will be coming out by the end of the year, as well as an online visualization tool that can let users explore cancer risk and source apportionment across the state. Thank you for your attention. I'll take any questions.
Thanks. That's very interesting. I was just curious because you'd mentioned kind of air tox screen at the national scale in the beginning, and I was wondering, a lot of that data makes its way into like tools like EJ Screen, and I was wondering if the modeling and stuff you've done here makes its way into tools like Cal Enviro Screen or other things that are kind of public facing that people can interact with. Just curious.
Yeah, thanks for the question. So I believe there has been talks between us and the Cal Enviro Screen for potential integrating part of our results into their assessment, the public facing website. But yeah, my manager will know more about this. Thanks.
Next speaker is Robert Mbiake, a professor at the University of Douala, where he works on air pollutants and their health impacts. I will turn it over to him for his talk and then come back to facilitate questions.
Okay, that my presentation concerns the impact of air pollution on the health of inhabitants in the city of Douala in Cameroon. We lead this work because we see that more people don't know exactly what is going on about air pollution. Next, please. And we try. Next. So, as an introduction, nowadays it's clear that the first victim of the poor quality of the air is the human health before the environment. In Africa, more than 70% urban sub-Sahara inhabitants are victims of the worst air quality. World Bank and WHO established that with 5.5 million deaths in this geographic area, air pollution kills more than HIV and malaria. Let's understanding that clearly that Africa is the main victim of this drama and pays the heaviest stripes. In the case of the city of Douala, with its 4 million inhabitants, the culprit of this air pollution are the rapid population growth with anarchic urbanization, the old car purchased in second hand, most of them, 80%, are old more than 10 years. To those second car, we can add at least 300,000 motorbikes. The quality of the road, non-asphalted, with it inject a lot of dust in the air. And this dust is made up with PM particulate matters. The fuel station that sell oil with some natural constituent crude as lead, higher sulfur, diesel, and gasoline with its additive. And at last, the wood and coal fire, because they use it to cook, to the stove cook for food along the roadside. Please, next. Next. In this picture, we try to illustrate how the atmosphere is polluted here in Africa, particularly in Douala. On the top, the first line, you said that it's wood and charcoal stock for cooking for along the roadside. So in Africa, particularly in the main city, air is polluted by the quality of the activities. And you see on the second level, you see those motorbikes, you see the quality of the phone, people are under it. You have the crossroad where people is congratulated for their work. And around them, people are leading more activities. That show how many people can be exposed for the quality of the air. So this photo is sufficiently illustrate that the source of pollution found in Africa are not the same as in the West Side or in Europe. Therefore, there is a need for a clear and original approach in the study of this pollutant. Next, please. Before leading a research on the impact, we try to be sure that to have the proof that the quality of the air in Douala was very worse, the air was polluted. So we make some measurement. So before the aspect of the impact of air pollution on the health, we first measure the concentration of some pollutant in the city of Douala, particulate matters, and molecules such as those you see on the screen. These measurements were conducted at two main crossroads. We have many crossroads in Douala, and we put our devices in two main crossroads and at the electrical thermal plant, because the plant is the place where the pollution is very important. And to be sure that the space have the same level of pollution, we make a tower around the city under the bike. We get back behind the back with the device, and we run about 40 kilometers inside the town during 20 minutes. That let us have an idea of the quality of the air in space. On your left, you see we have the dust track apparatus device we use to make the measurement of particulate matter. And on your right, you have a agar passive sample we use to measure the molecules. The next, please. After analyzing the data collected during our campaign, it appears that the city of Douala is actually polluted by particulate matters, as anyone can notice on this result. In space, because our measurement was in space and time, sorry, around the space in Douala, what the quality of the air in time from 1 a.m. to 23 p.m., what the quality of air. In time, we try to see the quality of the air. So in space, the average value found for PM was 7 times higher than threshold set by WHO. In time, for PM10, the average value was 5 times higher. And for PM2.5, the average was 2 times higher than the threshold set by WHO. That convinced us that the atmosphere, the quality of the world is not good. And so now the next time, after this proof, the next step of our research to try to see how this quality of air can impact the health. Next, please. So to study the impact of the quality of the air, we use this methodology. We adopted this methodology to assess the impact of the air pollution on the inhabitants of the city of Douala. We proposed a questionnaire that was supposed to make it possible to establish a correlation between the clinical manifestation felt by the interviewees and the pollutant to which they will have been subjected. How we made up the questionnaire? The questionnaire was administered through about 20 to 25 minutes discussion and structured around 3 components. The first component was to identify the interview and its characteristics such as gender, age, and school level. The second component was the clinical manifestation felt by those people who was under air pollution. And the third component was to record different risk factors and the exposure duration of interviews. The last one to try to see if there is any confusing confounders about those risks and the manifestation. The second step in the methodology, we try to see between all the population we have in our city, which of them was really exposed to the air pollution. So to conduct the survey through this interview, we decide to select the most exposure person dealing with these activities. We select the motorbike riders, the outdoor workers, indoor workers, and fuel station sellers. That is the 4 type of group of person who we were sure that they was exposed to the air pollution. Next, please. So the main result, to go quick, I try to just to resume the result. We distribute about 25 interview forms, and 1,723 of them were completed. The first, as I said, the first component, let us identify the people surveyed. Among the 1,723 interviews person, the gender male was enough. About 91% was male. The workplace, those are working place, those are outdoor worker, indoor worker. We have the motorbike riders, the most people was working outside. That we see it's about 1,311. So about 70% of the interviews was the motorbike riders. After this identification, and before that, the school level is important to understand the sociology in Africa. When you see the school level, those persons are facing with this problem of air pollution, you have about 75% of the interview have at least high school and university level. It is important to understand some practical problem we have here in Africa. After this identification, we try also to identify the the clinical manifestation. 16 clinical manifestations were selected and divided in two groups according to the sensitive part of the body. 5 manifesting at the level of upper respiratory part, you see, called nostril, throat pain, fever, and sinusite. 5 at the level of the lower respiratory part, and 6 as classic symptom. We can find anywhere. You have these classic symptoms like general tiredness, headache, eyes pain, lacrimation, conjunctivitis, and dizziness. That at this level, the first stage of our research was to select the clinical manifestation those interviewees can felt, and then separate them in three groups. The next, please. So after studying, we used a statistical method with confidence interval. 95% showed that from the 16 manifestations initially identified, 6 were regularly felt and seated. So we see on the table that on the upper respiratory part of the body, 2 types of symptom was regularly seated, cold and pungent nostril. Lower respiratory, we have 2, and classical symptom, we have 3: headache, eyes pain, and general tiredness. So when we make this separation between the manifestation and the parts of the body. So now the next step of the research was to be sure that there is no confounder. We make some confounder tests to avoid if there is any interaction between, for instance, the professional activities and the symptoms that the interviews felt. So to do this research, we use the Pearson exact independent text with p-value less than 0.05. It came out that the symptom felt did not depend on the professional exercise by the interviews. That means, as we separate all the person who make the interviews in 4 groups, there was not useful to do it, because if you take some example, for the dry coat, the dry coat did not manifest itself in motorbike rider more than in outdoor worker or fuel station seller. This result led us to regroup all the interviews of our study in a single group. The next, please. The next page. Please, next page. So after this, we conclude this. Outdoor pollution has a greater impact on the male gender, which exercises occupation related to the physical endurance, while women are more exposed to indoor pollution through their activities, which are mainly culinary. The second point is that one explanation for the higher proportion of young people exposed to air pollution is that they are underemployed in Africa, yet their school enrollment is high enough. That to explain that, despite that in Africa, young men, the youth went to school, with the fact that there is no employed, they do this type of work, motorbike riders, because they don't have anything else, and that's the reason most of them are. When you see the range, you see that most of the person that have those manifestations as about 22 and 27 years old. The third aspect is that tobacco and alcohol are a risk factor for the health related to the air pollution. Despite the small number of people who smoke, they are more likely to be confused by smoking. And we were surprised that between the person that fill the form, we find more than 20 of them with about 65 to 75 years old. That means that let's say that age is a confounding factor. 3 of 6 clinical symptoms failed. So those old people felt particularly some type of symptoms. Finally, we can say that air pollution is an aggravating factor for many diseases, especially since people exposed are alcoholic and smokers. Moreover, if they are elderly. Thank you so much for your attention.
Thank you so much for the presentation, Robert. So I just have a quick question about the survey. There was a very, very large majority of the respondents were male. So I wanted to ask if you have an understanding of why it's so biased towards male, why there were so few respondents that were female, and how that might impact your results.
Impact the result because we put a strategy to be very close to those persons. Because moreover, sometimes we was obliged to pay. So to fill the form, we can give some money to help them. And by the time when they understand the importance of the interview, they was very happy to know that they can have more information about the state of their health. So then after, because they are organized here in a group, and the chief of group was the one who take the form and distribute to the colleagues and said, try to answer to fill the form because it is important. In our mind, we want to pursue this research, going over and try to have a connection with the government to explain that this is the situation of the air pollution concerning the inhabitants, and what can we put in place to reduce the impact or to educate people to know that they are living in a polluted atmosphere, what we can do together to let them change their habits and so on.
Let's thank Robert one more time. We're going to move on to our last speaker. Thank you.
Okay, thank you.
Our next speaker is Sarika Kulkarni, who's an air pollution specialist at California Air Resources Board, and she'll be talking about PM 2.5 and health.
Hey everyone, for sticking around before going to the break. So I'm going to briefly talk about particulate matter precursor emission sensitivities and how it impacts air quality in California. So, as most of you have seen today, California has many of the PM 2.5 non-attainment areas, the highlighted in red. These are for the current annual PM 2.5 standard of 12 micrograms per meter cube, and primarily being San Joaquin Valley and San Joaquin Valley and the South Coast highlighted in the red. This standard is in the process of being revised to a value between 8 and 11. So if the value goes down to 10 micrograms per meter cube, then we'll have other non-attainment areas in California in the gold. And if it goes down further to 8, we'll have all the greens. So pretty much we are looking at many additional non-attainment areas in California. And this means a lot more emission targets assessment. So we started looking at the projected emission estimates from now, like about 20 years. So as you can see in the summary here, we are looking at all the 5 major precursor species for PM 2.5 formation: NOx, PM 2.5, ammonia, SOx, and ROG. And majority of them would be the NOx controls, which will bring down the emissions by about 45%. And what does these numbers mean for like the concentration changes? So to do this, we did a modeling assessment with using WRF and CMAQ. And here is our model general details. We used the CMAQ model. The metrology came from a 3-nested WRF domain that's shown at the bottom right here. And then the black box is what we are using, and that's shown up on the top right. We have highlighted 3 of the major non-attainment areas of interest: the South Coast Air Basin, Sacramento non-attainment area, and San Joaquin Valley. For this work, we chose the base year 2018, future year of 37. And then here is a brief model performance snapshots. So this is on the left is the average daily maximum 8-hour ozone for summertime. And the right is the spatial distribution of average PM 2.5 for December 2018. We did annual runs, but in the interest of showing the spatial and seasonal patterns, we're showing this one. The model shows appreciable skill. It is able to capture all the hotspots for ozone and also PM 2.5 in the region. And then what does this mean in terms of the overall annual average PM 2.5 model performance? On the left, we show you the bias between comparison of model and observations. And as you can see, the model does capture the spatial variability pretty well, but the values are biased low. And we have a mean bias about minus 2.9 and a mean error. So now that we have confidence in the modeling framework, we went ahead and looked at the baseline and future emission impact on the simulated PM 2.5 concentration. So on the left, far left is the spatial distribution of the 2018 base year. But as you see, it's since we are going to move on to the human health effects later in the talk, all the concentrations from this point forward are weighted based on 2018 population. The panel in the center shows you the PM 2.5 distribution with the emission controls of 2037. And then the panel on the far right is the difference between the left and the middle panel. As you can see, overall in California, we see a reduction in PM 2.5, anywhere from approximately 0.5, minus 5 at max. But the majority of the decrease or declining PM 2.5 is over the Central Valley, which is what the emission controls are doing it. And then we moved on to see what does this mean in terms of public health impact. For this, we used the changes in concentrations from the CMAQ, ran it through the EPA's standard method for calculating the health assessment. We focused on mortality only here. I know all this work was described in earlier talks, so I can skim through it pretty quickly. We used a concentration response factor, 10% increase in mortality for every 10 micrograms per increase in concentrations. And then the VSL, we have seen this about 11 million in 2020 US dollars. To isolate the effect of just the air quality modeling, we use the same VSL population baseline mortality for both the years. And here we are showing the results of that analysis. As you can see, this is an overall improvement in air quality or health benefits. The panel on the left shows you the avoided premature deaths in 2037 and relative to 2018. And on the right is a table summarizing them by regional level. And as you can see, San Joaquin Valley, South Coast get the majority of the benefits, and then followed by the Sacramento Valley and rest of California. All in all, you're looking at 1,200 avoided premature deaths every year with the existing emission controls. However, as we all know, PM can be directly emitted or can be found in the atmosphere with the secondary PM precursors, SOx, NOx, and others. So to examine how the precursors change in the different regions within California, we did some emission precursor sensitivity runs. So as you see here, we focused again on the same 3 regions, and we did over the board 25% cut specific only to those regions and all the 5 precursor emissions. All in all, it was, and we did it for 2 years to see how this cut would in the current environment of 2018, and then in the future, because the NOx controls will change the chemical environment. So we will expect to see different behavior. So this is a composite of like total 30 annual simulations. We have done it on, in the interest of time, we are showing the precursor sensitivity maps for the LA South Coast Air Basin. And all this is for the summary annual average again for 2018. The top left is the actual concentration, and the rest of the panels are the delta changes in concentration relative to those. As you can see, the directly emitted PM controls have expectedly the largest decline or decreasing concentrations, but rest of them do. All in all the precursors bring down the PM 2.5 in LA South Coast. What does this look for the future 2037? The general pattern looks almost across the same, except that there are some subtle differences in the secondary precursors like NOx, ammonia, ROG, and SOx. And what does this mean again in terms of the health benefits? So here we took the next steps to calculate the health benefits per ton of each of those emissions, which is we estimated them using the avoided mortality and then multiplied it by the BSL and then the delta change in emission concentrations. As expected, the PM, direct PM would give you the most benefits in terms of health benefits per ton. However, all the other secondary PM components also play a bigger role as they evolve. And NOx tends to have the most benefit in almost all the regions. One thing to note is the NOx benefits tend to get progressively better in terms of 2037 versus 28, the numbers. And we do have probably some numerical artifacts like SOx, we have a disbenefit, like it's not going to give you the expected outcomes. So, and one caveat here is we just got this framework going. It's a kind of a proof of concept work. So we're just taking it more. So this is where we are in all the regions. And in conclusions, we are gonna summarize that the simulated PM 2.5 concentrations generally show an overall decrease over California with the projected 2037 emissions, decreasing up to 0.5 micrograms per meter cube PM level, which translates to about 1,200 premature deaths per year. In this particular analysis, we have found that the 25% cut emissions for 2018 and 2037 identified primary PM, which is expected, and NOx as the limiting precursors for PM 2.5 formation in all these 3 regions of interest. And the predicted PM 2.5 from NOx shows higher health benefits per ton in 2037 than 2018 using the same set of emissions. That's pretty much what we have, a general assessment. And I'd like to acknowledge my colleagues for working on the Meng biogenics, providing us the gridded emissions inventory, and the COPS high performance computing cluster for providing the computer resources to do this work. And I'll be happy to take any questions. And I stayed on time.
Great talk and thanks for doing this work. And actually, you got the slide up now. So Ben and I were just trying to figure out the negative health benefit for SOx reduction. Is that because you're getting replacement of sulfate for ammonium nitrate in that location?
As I said, it's still a preliminary
Oh.
findings. But what we anticipate is, we haven't looked at deep dive, but we think the SOx power point sources in the Sacramento area, they're not very big. And when we are applying the same 25% cut, we think didn't overcome the numerical artifact in the modeling. So, but we'll look it up into further.
Okay, sounds good.
We have time for one more question. I was going to ask for your 2037 numbers. Do those include regulations that are already on the books and approved, or are you also including regulations that are proposed and likely to go through?
I believe I'll have, it's all that are approved, but not some of the ones that are in progress. So we'll have more controls like the state control strategies, the regional ones and all, but this is our best estimate at this point.
Thanks. All right. Since we are basically at our time and ahead of a break, we'll thank Sarika one more time. And so we're on break now and we'll return at 2:45 to continue this session.